Hello Block C, and listen up, Jackie Lang. We're going to be studying some indicators, and we're going to be talking about what an indicator is and how do they work. So the first thing we need to say is, what is an indicator? An indicator is a weak organic acid, and with different colors for its conjugate acid and conjugate base forms. So here's an example of a very common indicator. IN right here stands for indicator, and IN right here is indicator, and it's an acid. So one form has an extra proton. Okay, so here's the acid form of this indicator, and here's the base form of this indicator. Okay, now how an indicator works is that one form is one color and the other form is another color. So example, HIN, or the acid form of this indicator, is yellow, and the acid form of this of its conjugate base is red. So what happens if this indicator, a very small amount, is placed into a basic solution? We're going to look what happens. So when it's in a basic solution, the H3O plus concentration is very low. Okay, so if this is very low, okay, what is going to happen? Well, it's going to, if this is very low, it's going to shift to the right. So if H3O plus is low, it shifts right. Shifts right, and therefore it becomes red. Therefore it becomes red. Okay. In other words, the reason why it's red is because the concentration of HIN is less than the concentration of IN. Or in other words, the concentration of yellow is much, much smaller than the concentration of red. And that's why when it's in a basic solution it looks red, because the concentration of red is much higher. This right here is red, while this is yellow. Okay? Now, when it's in an acidic solution, the concentration of H3O plus is quite high. Okay? So instead it increases. This is very, very high, and since this is very high, it shifts to the left. Shifts left, and therefore it becomes yellow. Okay, or in other words, the concentration of HIN is greater than the concentration of IN minus. This B minus up there. And this is why, or in other words, since HIN is yellow, the concentration of yellow is greater than the concentration of red. Okay? And that's why it becomes yellow. Okay? Now, what happens when the concentration of HIN is equal to the concentration of IN minus. Well, then you get yellow. The concentration of yellow is equal to the concentration of red. And so your solution is half yellow and half red. Solution is then orange, a mixture of yellow and red. Orange. Okay. And when the concentration of HIN is equal to the concentration of IN, this is called a endpoint. Okay? That's called an endpoint when these are equal. Or often many people call it a transition point. Transition means the point at where it's turning. The point between when it's turning from yellow to red. So it's transitioning, and the transition point is orange. Okay, so we call it a transition point. And that's just when an indicator is when the concentration of HIN is equal to the concentration of IN. It does not mean stoichiometric equivalence point. It does not mean like it's titrated perfectly, or it does not mean it's neutral. It just means the concentration of HIN is equal to IN. And it's also, and how you tell this, it's a mixture of these two colors. And indicators can be many different colors, and we'll look at some different indicators later on. Okay. Now, let's look at a few questions of what we can do. Okay. Oh, before we do, let's take a look at something else. Another thing too is let's come up with a now that we know that what a transition point is. Okay, when transition point is a transition point, again, I'm just going to write this here, is HIN is equal to the concentration of IN minus. So, at what pH is the transition point? Okay, and we can calculate that. Let's make, this is an acid, so let's write a Ka formula for this. Ka equals products IN times H3O plus, this is a liquid so we don't count it, divided by HIN. So if it's at the transition point, okay, and we want to know what pH it is at the transition point, what we can figure out is, well, at transition point HIN is equal to IN, so this and this are going to be equal, so they're going to cancel. So Ka is going to equal the concentration of H3O plus at the transition point. Okay. Now, if we want to find out what pH this transition point is, well, we can just take the negative log of the Ka and the negative log of the concentration of H3O plus, and in other words, what we get is pKa equals the pH. Okay, and so what this is like the pH of the transition point of an indicator. Okay, so let's look at a few questions and figure some stuff out. Okay, right here it says an indicator is red at pH 3.8 and yellow at pH greater than 4.4. What is the Ka for this indicator? So, if we were to draw like kind of a line graph right here, we'd see that if here's 7 somewhere in the middle and here's 0 and 14, this is red at less than 3.8, so it's red here, okay, and it's yellow at more than 4.4. Okay, and in the middle right here it's orange. So the question is, there's a bit of a transition point, but we want to find the exact middle point, or in other words the midpoint. So what we can do is, to find this midpoint right here, what we can do is we can just go 3.8 plus 4.4 divided by 2, and we see that this equals, well, these two is 8.2 over 2, which equals 4.1. So the midpoint of this is 4.1. Now, it says, what is the Ka for this indicator? Well, if we know that pKa equals the pH of the midpoint, well, we can just take, or in other words, pKa equals 4.1. If we want to find Ka, we can just do the negative, we can take the anti-log of this. Okay, so what we can do is we can go 10 to the minus 4.1, and that's going to equal our Ka. Okay, and I've done this one already. So our Ka equals, again, this is one significant figure, and so our Ka equals 8 times 10 to the minus 5, and that's the Ka of our indicator. Okay. Now here's another question. It says, an indicator changes from yellow to red at pH 11.0. What color is it at 1.0 times 10 to the minus 4? So, again, I'm going to draw a little bit of a kind of a graph here. Here's 14. Here's 0. And it changes from yellow, and here is about 11, and then it goes to red. Okay, and it does that, it changes at pH, so it gives us the midpoint. Now it says, what color is it in a 1.0 times 10 to the minus 4 molarity of NaOH? Well, what we know about NaOH is that it is a strong base, okay? And so it's going to 100% ionize, and therefore we know the concentration of OH is also 1.0 times 10 to the minus 4. So, what we can find out is, we can find the pH of this, okay? And I'm going to combine two formulas right here. The first formula I'm going to do is I'm going to use this formula right here. Kw equals H3O plus times OH minus. Okay, and I'm going to solve for the concentration of H3O plus. And that's going to equal 1.0 times 10 to the minus 14. Okay, that's our Kw value. Our OH is given to us, and that's 1.0 times 10 to the minus 4. And that's what H3O plus equals. Okay, I'm going to take this and I'm going to put it into my pH formula. pH equals the negative log of H3O plus. Now, since these things are equal, I'm just going to take this and stick it right into there. So what's going to happen is that pH equals negative log Kw over our concentration of OH okay, and we don't even need a calculator for this one because this is going to be 1.0 times 10 to the minus 10, and if we take the negative log of that, pH equals 10, okay, or in other words, pH is, this is 2 sig figs and 2 sig figs, and so pH is going to equal 10.00, okay, and so where does that fall on this graph right here? Well, if this is the pH of our solution, that's going to fall right about there, okay? And so what color is it going to be? It's going to be yellow. So therefore, solution is yellow. Okay?